Hi everyone, Dr. Gray here. Today we are working on waves target 4. Understanding how waves act and interact, understands the behavior of waves is caused by reflection, refraction, and absorption, and understands how reflection and absorption produce color. And today we're going to be focusing on how waves act and interact. We're going to focus specifically on the behavior known as diffraction. So what is diffraction? Well, diffraction is the bending of a wave that occurs when the wave encounters a barrier. What I want you to see right away is that the definitions for diffraction and refraction are very similar. In both cases, we have the bending of a wave. In diffraction, the bending is caused by a barrier, and if you'll recall, in refraction, the bending is caused when the wave encounters a new medium. And so you want to be careful in your use of these two words. One of the things that helps me to remember that diffraction is the bending of a wave that goes with barriers is that diffraction and barrier both start with letters that are pretty early in the alphabet, whereas refraction and medium, because it's about the medium or the change in medium for refraction and medium have letters that are later on in the alphabet. So maybe that'll help you as well. So let's look at some examples of diffraction. Here in our first picture here, we have the wave that we're looking at are light waves or visible light, and our barrier in this case are the clouds. And you can see how the cloud, if you look at the rays of light as they're coming through those clouds, you can see that they are spread out. In other words, they're going this way and they're going this way. They don't have that parallel fashion that light waves usually exist in. If we look at our next example over here, so this is a picture taken of probably a wave tank. So the waves here that we're looking at are water waves, and our barrier in this case is this wall, and there's this opening in the wall here. In our last example here at the bottom, again we have water waves, and here, so this is just a picture that someone has taken probably of some coastal area. Again, our barrier is the rocks. We're looking at the opening in the rocks, and you can certainly see here how the waves are curved, right? They're coming in, and the crests would all be parallel. In other words, our waves, our rays would be parallel, but as they're coming through this opening, now you can see that it's curved, and so our waves have been spread apart by that barrier. So we can draw ray diagrams for diffraction, similar to how we drew ray diagrams for refraction and reflection. In this first picture that we're looking at a wave table. We're looking down on the wave table, so we're viewing everything from above. And in this picture, before the barrier, the waves are all parallel. And so if we look over on the right-hand side here, the way that we represent parallel waves or parallel crests is that we draw them with arrows, which are our rays, that are also parallel. And then after the waves have passed through the opening here, you can clearly see now that the crests and the troughs are no longer parallel. Well, they're sort of parallel, but now they're curved. They're not linear. They move, the crests and troughs have now been curved by moving through that barrier. And so over here on the right-hand side, here's our ray diagram. And so we represent that curving of the waves, or that diffraction of the waves, by fanning out those arrows so that they're no longer parallel. But how much should we bend them? How much should we curve those waves? Or likewise, how much should we fan out those rays to represent diffraction? Well, the amount of diffraction that a wave experiences depends on two factors. The amount of diffraction depends on the wavelength of the wave and the aperture size. And aperture size is just the size of the opening. In the barrier there. Now, diffraction only occurs, this is key here, diffraction only occurs when the wavelength of the wave is similar to the size of the opening. Now, let me give you a practical example of when you've probably experienced this. So imagine that you are imagine that you're in Mr. Anderson's room for English. And I've done a demonstration for my chemistry class, and my door is open. Now, this demonstration was so cool that my chemistry class claps and wow, and you can hear them clap and say wow and express their excitement, but you can't see what happened. And so the reason why you can hear the results, but you can't see what's going on in another room, is because the wavelength of light waves and the wavelength of sound waves are very different. The wavelength of light waves is in the nanometer range. It ranges from 400 nanometers to 700 nanometers, whereas sound waves are in the meter range. So it takes 1 billion nanometers to equal 1 meter. So the wavelength of light is tiny. I mean, it's less than the diameter of a human hair. Whereas the wavelength of human voices is about the width of that doorway. And so because the wavelength of the sound is similar to the size of that opening, the doorway in that wall. The wall is the barrier, the doorway is the aperture or the opening. And because the sound wave is similar to that size or that opening size, sound waves are bent. They are refracted as they pass through that door, as they move through that door. And so it allows those sounds to be bent around corners. Light, on the other hand, the wavelength of light is 1 billion times smaller than the opening of that door. And so the light waves are not bent. And because they're not bent, they only experience diffuse reflection. Let me try that again. Diffuse reflection. And so you can't see them. You can hear sounds coming from another room, but not see the source of the sounds coming from another room because of the wavelength or the differences in wavelength of those two waves. The wavelength of the wave must be similar in size to the opening in order for diffraction to occur. If the wavelength of the wave is much, much smaller than the size of the opening, no bending, no diffraction occurs. Let's see if we can look at that another way. The diameter of a human hair is about, so this distance here, is about 17 micrometers. And that's if you have very fine hair. The wavelength of red light, and we can see here that the wavelength of red light is the largest of all of the different colors of light. The wavelength of red light in micrometers, this is 0.7 micrometers. And so the diameter of a human hair is 100 to 200 times greater than the wavelength of red light. And so again, the reason that we cannot see around corners is because light waves are not bent by corners. They're not bent by large openings in barriers like doorways or openings to hallways. Sound waves are. Sound waves are very similar in size to the opening of doorways or the width of hallways. And so sound waves are bent. We can hear sounds around corners, but we cannot see sounds around corners because of the difference in wavelength. Let's look at another example of this. You have probably, at some point, experienced sitting outside and a car drives down the road in front of you and you hear the bass beat of that car thumping as it goes by the road, but you can't hear anything else. Now, the odds are the person driving that car is not just listening to someone beating a drum. They are probably listening to an actual song where there are high notes as well as those low bass notes. Well, why can we not hear the treble? Why can we only hear the bass of that vehicle from that vehicle that's driving down the road? Well, it comes again to the difference between the wavelengths of high-pitched sounds and low-pitched sounds. So when it comes to sound, pitch correlates with frequency. And so high frequency sounds, those are our high pitch. High frequency equals high pitch. Those are the high notes. La 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 la. Low frequency sounds, those are our low pitch sounds, our deep sounds. Low pitch. La 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 la. Now, remember, the relationship between frequency and wavelength varies indirectly. So high frequency or high pitch means low. So now let's look at another example where diffraction plays a role. Translucent fabric. So translucent means that some light is allowed through, but the image or there's not enough light coming through for us to be able to clearly make out what's on the other side of that translucent object. Translucent is opposed as compared to transparent. A glass window is transparent. Light comes through and you can clearly see the image on the other side. Translucent, like the image that we have over here, we can see that there is someone standing on the other side. I'm going to go out on a limb here and I'm going to say I think it's probably a guy standing on the other side because I don't see much in the way of hair up here. But there's no way to be sure because it's not a detailed image. It is a kind of blurred image. And so, well, why is that image blurred? Why, in this case, what is it about a translucent object that allows some light to pass through, but not detailed images to pass through? Well, if we think about, let's imagine that this guy is standing behind a curtain. And when it comes to curtains in all fabrics are made out of woven material. And so in that weaving, or during the process of weaving, there are little tiny holes that are left between the individual fibers. And remember, light waves are the wavelength of light waves are extremely tiny. They can kind of scooch their way through anything, but when they pass through these holes, they're being diffracted. And so the light wave is passing through this hole, and as it passes through, it's being diffracted outward. And because the light waves that are passing through the object are not parallel, because they are diffracted and spread out, or we might think of them as being diffused, the image that we see, just like when we're looking at diffuse reflection, the image is not clear. If you think back to when we were learning about the different types of reflection, there's specular reflection and diffuse reflection. In specular reflection, like when you look at a picture or the image of yourself in a mirror, that mirror is perfectly smooth. And so those parallel incoming or the parallel incident light waves, when they are reflected, they are also parallel. And because that reflected light, or the waves of that reflected light, are all parallel, we see a nice clear image. In diffuse reflection, this is maybe why can you not see your reflection when you look in your t-shirt? Well, it's because the surface of that t-shirt is not perfectly smooth. It's bumpy, it's sort of rough like our picture here. And our incoming light waves are always parallel. Our incident light waves are parallel, but now they're not reflected in a parallel fashion. This one is going to be reflected in this direction, and this one's going to be reflected in this direction, and this one's deflected in this direction. And because these reflected rays are not parallel, all we see is the color of the shirt. Our eyes get some information, but not enough information to see our reflection in our t-shirt. And again, it's because those light waves are not parallel. And so during diffraction, it's a similar case. Because the light waves are diffused or diffracted when they pass through that opening and they're no longer parallel, we don't get a clear image. We get a blurred image. And so that's what we see. That's why the guy standing behind this curtain is just a blurry image. We don't know anything more about it than we know for sure that there's a person standing behind there, but that's all that we can say about what's going on there. The last example that I want to talk with you about today regarding where do we see diffraction comes down to shadows. So If you look closely at shadows, particularly shadows outside, inside it's hard to see. In the classroom, it's really hard to see because there are multiple lights in the classroom, and so you get, if you've got 2 lights, you get 2 shadows that overlap. If you've got 10 lights, you get 10 shadows that overlap. When you're outside, there's just one sun, so there's just one shadow, which makes it a little easier to see this phenomena outside. But let's look in the picture of the trees here down in the bottom right corner. If we look at the picture that's taken, the trees, the edges of the trees, at least from our perspective, are nice and smooth. But if you look at the shadow that's on the ground, the edge of that shadow is blurred. That blurring of the edge of the shadows, and we see it all over the place. It happens here. You can certainly see it over here. The blurring of the edges of those shadows is a result of diffraction. Now, the barrier is the object that's creating the shadow. It's the object that's coming between the source of light, in this case our sun, and the ground, which is where the shadows are following. That object is the barrier, and the light waves are bending as they move around that barrier, and that's causing the edges of those shadows to blur. You can see it in the picture of the hand here. Right? These little, the fingers look a little bit fuzzy, and the same is true of the picture of the guy's head here. All around the edge of that profile, that shadow it kind of looks fuzzy. It's a little bit blurred, and that's because of diffraction. So that's it for today's lesson on diffraction. Your assignment now is to write me a paragraph summarizing what you have learned about diffraction. I want to know what is happening to the wave during diffraction. Tell me what the action of that wave is, or how that movement of that wave changes. What are the 2 factors affecting the amount of diffraction? So what is it you would change if you wanted to increase the amount of diffraction, or what are the things that determine whether and how much waves are diffracted? And then, last but not least, put into your own words. Tell me why is it you can hear voices coming from another room, even though you can't see the people talking? And as always, please let me know, what did you find most interesting about diffracted waves? Is there anything else you want to know about diffracted waves? Is there any other phenomena that you wonder, is this an example of diffraction? Please feel free to ask those and just include that in your summary paragraph. That's it for today. We'll see you in class.